All right, hello, and welcome to a special panel discussion in celebration of Dark Matter Day 2020. Each year, on and around October 31st, the world celebrates the hunt for the unseen, an elusive substance that scientists refer to as dark matter. Dark Matter Day is a globally recognized celebration of the cosmic riddle of dark matter. Local events organized by institutions and individuals around the planet explore dark matter's mysteries and highlight the experiments that bring us closer to illuminating them. My name is Stu Shepherd, and I'm the Communications Specialist here at TRIUMF, Canada's Particle Accelerator Centre. With me are three panelists, each with a unique perspective on the hunt for dark matter. And we're going to talk a little bit about what dark matter is, how we search for it, and what we've learned along the way. So, without further ado, let me introduce our Dark Matter Day panel discussion participants. Our first panelist is Djuna Croon. Dr. Djuna Croon is a postdoctoral researcher in theoretical physics, and also a current member of the TRIUMF Theory Department. Her work is focused not only on dark matter, but also diverse topics in cosmic inflation, the extended Higgs sector, boson stars, phase transitions, supernova explosions, black holes, gravitational microlensing, and gravitational waves. Djuna is also an accomplished science communicator and an advocate for inclusive, accessible science. Our second panelist is Richard Germond. Richard is a graduate student and Ph.D. candidate with Queen's University, currently working as part of the Canadian SuperCDMS group, the Cryogenic Dark Matter Search that is underway at the TRIUMF-partnered Snow Lab in Sudbury, Ontario. Richard and the SuperCDMS team are part of a wider hunt for dark matter that leverages ultra-cold inert materials that, upon interaction with an incident dark matter particle, might provide our first glimpse of the true nature of dark matter. And our third panelist is Reiner Kruecken. Dr. Reiner Kruecken is TRIUMF's Deputy Director of Research. Reiner oversees TRIUMF's participation in a wide variety of particle physics experiments and collaborations, including contributions to dark matter experiments. Reiner achieved his master's and doctoral degrees in experimental nuclear physics from the University of Cologne, and currently serves as a professor of physics at the University of British Columbia. Reiner has led TRIUMF's contribution within the wider Canadian effort to develop a low-cost ventilator for COVID-19 patients as part of the Global Mechanical Ventilator Milano collaboration, a project that is based on principles and expertise derived from the dark matter experiment, the Global Argon Dark Matter Collaboration. So, I'm ready to get started. I'd like to start with a quote from Fabiola Giannotti, who, as some of you may know, is the current Director General at CERN, the European Organization for Nuclear Research, which oversees the Large Hadron Collider and associated complex of high-energy physics experiments. Of dark matter, Fabiola once said, "Dark matter is everywhere. It's in this very room." And I think that speaks to something very intriguing about not only dark matter, but a variety of phenomena in particle and nuclear physics. And I'm interested in hearing what each of you thinks of that when you hear that quote. Maybe we can start with Djuna.
Yeah, right. Yeah, that's a very interesting quote. Dark matter is indeed everywhere, in the galaxy, at least, in galaxies. And not only is it everywhere, it's also moving very fast. So it's in this very room and it's moving very fast through this room. Something about like 800 kilometers an hour, so very fast. And the way it makes me feel, what it makes me think is that it is actually in our grasp. You know, we know quite a lot about it already. We know that there's quite a lot of it. You know, we know how fast it's moving. We should be able to detect what it is. So it makes me hopeful.
That's a great description. Richard, what do you think of that quote, "Dark matter is everywhere. It's in this very room"?
Yeah, I mean, I also think it's a really great quote. And I think you can kind of tell that she's an experimentalist when you hear this quote, because that's kind of how we look at it too, you know, like, oh yeah, the dark matter is right here in this room now, if only we could measure it. But as Djuna says, I think we are finally getting to the point where it's hopefully within our grasp. So, you know, maybe within the next decade or two, we see something, and that would be really exciting.
Thanks for that. And Reiner, do you have anything you'd like to add to that?
Well, I think Djuna and Richard have already described it very well. To me, it sort of is expresses really the fascination and the mystery of our universe and the world of subatomic particles, which are all around us, our world is made of, but we don't experience. And dark matter or neutrinos, but even the particles that make up the atomic nucleus are so mysterious to us, and we can't experience them directly. But they're right here. They're right there in front of us, and it's really the skillful experimenters and the innovations that come with these experiments that bring this out, and it's great to be a part of that effort, which is really worldwide.
Yeah, well said. And before we delve further into some of these other questions about dark matter, maybe Reiner, could you provide us with sort of a high-level explanation of what dark matter is, or what we think it might be?
I can give it a try. So in a nutshell, dark matter is just different from our normal matter that surrounds us and that you can experience, you can touch, or we can see in the lights of stars and galaxies, and even the gas clouds in our universe. Because dark matter does not reflect light, it doesn't absorb light, it doesn't emit light, so it stays dark to us. And that's why we call it dark matter, and basically also showing our ignorance a little bit and not knowing what it actually is. The fact that it does exist, we can see in the effect it has through the gravitation of itself on the motion of stars and galaxies. And so we can really see how it's only possible to explain the motion of these stars and galaxies if we assume that there is something else out there, that there is this dark matter out there. And it really outweighs actually normal matter by a ratio of 6:1. So there's a lot more dark matter out there than the matter we usually experience. So that's quite awesome, I think. But we really don't know what it is made of. We think it might be new type of elementary particles. We don't know if it's just one or it's a family of particles. But it could also be a change in the laws of physics as we know them, and just show its effect this way. And we haven't figured this out, and so it's a very fun topic to investigate.
Thanks for that. If Djuna or Richard, if you have anything you'd like to add about sort of your interpretation, your high-level explanation about what dark matter is, I'd be curious to hear that as well.
Yeah, I can go ahead. So what I would say is, like, one thing that we all experience is our attraction to the Earth. That's gravity, and it just means that, like, if you jump, you'll come down at some point. So the Earth is also attracted to the sun in turn, and that means that it will orbit the sun and it won't just fly away. And then the sun in turn is attracted to the center of the galaxy, and that means that it will orbit the center of the galaxy. Now, as a physicist, what you can do is you can take all of the stuff that you can see in the galaxy, so that's stars, planets, stellar remnants, mostly stars, and you calculate the gravitational the gravitational force due to it. And if you do that, you just come up empty. You just don't have quite enough to explain the rotation of the sun around the center of the galaxy. And so that means that there's something else. In fact, it's not easy to explain the formation of the galaxy in the first place. So that means that the normal matter, the matter in the stars that I knew about that is interacting with light, isn't enough to explain the gravity. So there must be other stuff. And that's what dark matter is.
Well said. Yeah. Maybe building on that, Djuna is both a theoretical physicist who has studied dark matter and a science communicator. Can you describe for us the sort of the principal dilemma behind the search for dark matter? Why has it been so hard to illuminate? And I guess we've sort of covered this, but if there's anything you'd like to add about sort of the main difficulties in it.
So I think I wish I was able to answer that question, because that's actually a very hard question. So like I would like to know why it is that this particle exists, and at some point was produced, but it doesn't interact with the stuff that we know about very strongly. So that's actually kind of an interesting question. And so we have some ideas, we have models, but the principal dilemma is not just that, it doesn't interact strongly with light, we also need to explain why that is.
And Richard, as a member of a team that's currently searching for dark matter along one of these avenues or sort of proposed characteristics of dark matter, can you describe some of the challenges that are involved on the ground, sort of in the hunt for dark matter? Why is it that it poses such a challenge in terms of its characteristics and how we detect it amidst regular matter?
Yeah, sure. So as Djuna already said, it interacts very weakly with normal matter. So already you're looking for something where an interaction with dark matter and your standard model particle, your detector, that interaction is very rare. So you need to build detectors that are not only large, but that you can leave and have them just sit there for a long time while you wait for a dark matter particle to hit. The other challenge is that these dark matter interactions can actually deposit very small amounts of energy, and building detectors that are actually able to measure these small energy depositions is quite a challenge. The thing which kind of makes dark matter, even more challenging to detect is, as we mentioned earlier, there's all kinds of unseen particle phenomena happening around us, and those particles can interact in your detector and cause what we call background events. And so particles can be coming from space, like cosmic rays, or they can be dirty materials in your detector which undergo radioactive decays, and any of these can hit your detector. So because of that, careful design considerations need to be taken. For example, my experiments actually located 2 kilometers underground in a mine just to reduce the flux of cosmic rays. So there are quite a number of challenges, I'd say, but the number one is kind of reducing these background events in your detector.
And that's a pretty common theme among dark matter experiments, as I understand them. I've personally visited Sanford Underground Research Facility, which is also a mine in which it used to be, I think, a nickel mine, and it's been converted into a science complex, which is really interesting. Sort of on that topic of how we construct experiments and what we gain from them when we do, hunting for very faint particle interactions like those we expect for dark matter requires a pretty significant investment in engineering expertise and technology development alongside sort of the theoretical and the academic side. And it's really at a global scale. And this expertise has proven instrumental in tackling different problems, including recently actually combating the COVID-19 pandemic. Maybe, Reiner, can you describe for us, again, at sort of a high level, how the skills and expertise from experimental physics can translate to, say, the development of a ventilator for COVID-19 patients?
Absolutely. As Richard described already, the detectors to be able to find to search for dark matter and hopefully eventually find them are quite sophisticated. They're very large scale instrument. And typically you have some sort of detector materials. Often you have gas systems involved, like particularly the collaboration that started the ventilator project is involved with a liquid argon detector. So again, then they have the expertise in large scale and quite sophisticated gas management systems. You need expertise in electronic systems to read out signals, to really detect these faint signals from the detector. And so design and production of custom electronics to control the systems, to read out the detectors, but also then making displays of monitoring the detector, looking at the data, analyzing it, and having all these systems in place that they work for a long time, reliably, can be monitored. All of these aspects are actually aspects that one finds also in a ventilator in some way. You need to control gas that goes to the patient and comes out of the patient. You need to control the electronics and maybe build something, in our case, something specialized for the system. one needs to then display the data, control it, make something very reliable. And so all these expertise elements that helped us build these particle physics detectors are finding basically their way also in a ventilator project. And that would really enabled us within 6 months really to design and build and industrialize with industrial partners a medical ventilator that is now being produced for COVID patients.
It's incredible.
It's quite a ride, I can tell you.
Yeah.
we worked across 9 time zones around the clock, with people handing off literally around every day and morning. And everybody was just so happy to be involved in the humanitarian project and really make their work count for something more than just the fundamental science that usually drives us.
And also representative, to me at least, of the nature of science as we move forward through time. It's no longer individuals with sort of eureka moments, where most science now largely is global, in a lot of cases international collaborations with dozens or hundreds of members working at multiple institutions, and really I see that as a way that we enable solutions to global problems as well. So
that's a very good point. It's this international collaboration, and also if you look at the laboratories which hold the expertise in the technical engineering and physics scientific expertise that you can deploy in a global crisis for something else than what just the basic research that they're funded for. So in the case of TRIUMF, like, we deployed our engineering and technical skills to the project, and this could be done and has been done also for some other challenges already, and is something that is not often recognized enough by government or the general public.
Yeah, makes sense. I'd like to turn to Richard. I'd like to explore a little bit about your day-to-day as a member of sort of boots on the ground team hunting for dark matter. What does a day in the life of a dark matter hunter look like?
Yeah, well, what I can say is that there's typically a lot of variation, as I'm sure there is in a lot of research in general. But generally the day kind of starts with some meetings on the operations of the experiment or the analysis of the data. If the experiment's running, then generally I spend time taking data or managing the facility or doing some kind of analysis. But if the facility's down, then you're spending much more time doing analysis work or planning upgrades for the next run. When you actually go to the site, so when you go to SNOLAB, that's day's a bit different. You start around 5 in the morning, and then you drive out to the mine to get the elevator down at 6, and then you hike for about 1 kilometer to get to the mine and take your shower to go into the clean room and start your shift at 7. And then you're mostly, when you're at the lab, focused on changing out the detectors or moving over the facility in some way to prepare for the next run. And your day ends at 4. So that's pretty much a normal kind of day in the life.
It's a pretty diverse regimen for sure. I'd be curious to hear from Djuna as well. I mean, obviously a dark matter hunter from the theoretical side. What does your day-to-day look like?
Oh, yeah, it's an interesting question. So I think, obviously I don't go into a mine very regularly, but my other days seem kind of similar, I guess. I start off with meetings often. I'm not working in set collaborations, but I do work in collaborations. They're typically smaller, 3-4 people, sometimes 5. And they are also global. So for example, I have one collaboration now that consists of someone that's in Japan, another person on the West Coast, someone on the East Coast, and someone in the UK. And so that's actually really hard to find a time zone or a timing to meet in with these 4 different time zones at the moment. So typically I have meetings in the morning because I don't mind it and we're on the West Coast. Then I might have a few seminars during the day that I that either are TRIUMF seminars or journal clubs that I go to, or I give a talk myself. But then the rest of the day I spend learning. So I am doing a calculation, I'm following my curiosity, I'm working on the projects that I have the meetings about. Yeah, that's just really exciting for me. I'm reading around my topic. Every morning starts with checking all the new papers that are out that are of interest to me. So yeah, at the moment I do full-time research, so that is what I do every day, and it's beautiful.
Thank you. That sounds fascinating. Sticking with Djuna, I'm curious. In addition to your capacity as a theoretical physicist, you've pursued science communications and advocacy in a variety of channels. And in your experience, what is the best way to communicate some of the more complex details of a concept like dark matter to the general public?
Yeah, it's a good question. So I guess I think all of us have given sort of introductions to dark matter. I think these are good ways of kind of sort of explaining what it is. I think in addition to that, I would say, so how do we know that stuff is there? Well, one way is that it interacts with light, so it reflects light or it sends out light, and that light, we can see that in our eyes. These are photons that we detect. And then there are a few other ways to do with, for example, how our atoms are held together, and nuclei are held together. So it's via an interaction between particles that we know that a particle is there. And these are the ways that we're searching for dark matter as well. Now, we know that dark matter interacts in at least one way with the matter that we know about, and that's gravity. And we don't know nothing about dark matter because gravity already does tell us quite a bit. It will tell us, for example, how much dark matter we have, which I think is huge. And it also tells us to some extent, from when the dark matter must at least have been there already, and what role it played. But gravity doesn't seem to tell us much about how many kinds of dark matter particles there are. It doesn't care about how many particles there are, it seems. So that's why we're hoping that maybe it still interacts via the other ways that we know about, just very weakly. There's good reasons to think that must be so, because while dark matter and normal matter, there's different amounts of them, but they're kind of similar amounts. And that's kind of a big coincidence if there's no interaction between these different kinds of matter at all. And so that's how we hope to search for it. But we call it dark because it doesn't interact much with light, and it doesn't seem to interact much in other ways too.
Thanks for that. Yeah. I was just thinking as I listened to you there, I think we're very fortunate in that each of you is actually a very eloquent speaker with a great understanding of sort of how to communicate, which I think is a greater skill than most people understand. I remember when I first started at TRIUMF, I went home for Thanksgiving and I was trying to describe the ultra-cold neutron experiment, the search for the electric dipole moment of the neutron, to my average family members, like my aunts and my uncles. And I remember thinking, even just to be a scientist or a researcher, you develop an acumen in science communications just to be able to share your research with your closest friends and family. And again, I think we're very fortunate in that you have all sort of mastered that. Richard or Reiner, do you have anything else about sort of how you communicate these complex principles, let's say, to your families or friends? Do you have any sort of methodologies or tactics that you employ?
I certainly don't think I've mastered it, as you say, but I mean, some of the things you can do are, just avoid, technical terms. You can typically do without describing all of the nitty-gritty details of a detector or, of some theory, and you can just kind of give the broad concept. In my case, I don't need to describe, the inner workings of the detector. I can just say that what we look for is a particle interaction that deposits some heat, and ultimately this raises the temperature of our detector, and that's effectively what we measure. But you don't need to go into the you know, specifics.
Yeah, I think that's really important, and I mean analogies are very simple, typically not exactly accurate, but good analogies that people can sort of depict helps. I mean, I think as scientists we grow up to be precise in our language and make sure that we say exactly what we mean. And I'm always ruffled when somebody is imprecise, but that one has to sort of lose a bit in the science communication part, because you basically have to find hand-waving arguments to and analogies that sort of apply, even though they're not quite right, but they're good enough to actually for somebody else to get a feeling for the phenomenon you want to describe. I just was reminded of an analogy that isn't applied into dark matter so much, but if you want to resolve small structures, for example, with particle accelerator beams, you can compare it a bit like you have a picket fence, and you want to see, okay, if you actually throw a basketball against the picket fence, it will always bounce back. So you will actually never know that there is holes in the fence. But if you use particles which are smaller, like marbles, some of them will just go through, and others will bounce back. And that tells you, oh, there's holes in there. And from the number of holes and what particles you throw and how often, you can actually do something about the structure of the object that you're studying. Now, in this case, that is an analogy by just having higher energy particles being smaller probes, and therefore you can resolve with higher energy particles smaller structures in the universe or in the subatomic world. So these kind of simple analogies, I think, are pretty powerful, and everybody has sort of developed a set that they have used over time, and trying to find more when other people talk. So I'm always listening for and watching out for some that I can use.
I am too, as a science communicator. I definitely have a toolbox of mostly imprecise, but generally accessible analogies, which the public loves to hear, and members of the research community often do, sometimes not. But, as an area of study within the wider field of particle physics, dark matter research has a bit of a sort of mysterious connotation to it. And I'm interested to hear from each of you sort of what would be your advice to your early career student, to an early career student who wants to contribute to the wider dark matter search, just sort of recognizing the state of the search of dark matter versus, our understanding about other particle physics phenomena. So another way to think about the question I'm trying to get at here is, what advice would you give your former student selves before launching into your respective, scientific, academic, and professional roles? Maybe we can start with Reiner.
Okay. I mean, one has to, I think, understand that dark matter is one of the most foundational questions that are out there right now. We know it's there, and we believe that we're actually getting ever closer to discovering it, because we're pushing the limits with our detectors more and more. And so it's a fantastic time to actually get involved and be part of these great international teams to hopefully find it. Now, there is always the chance that one is not successful and one then sets limits on the existence. But even that is an important element and informs then theory, for example, on what it is not. And therefore, that is even that part is an important contribution as well. And along the way, one learns a tremendous amount in working in these international collaborations with very sophisticated technologies and different techniques, and one can really make, as a single person, a significant impact in learning a broad spectrum of techniques, and then applying them to this particular search. But then they can also be helpful either in an academic or a non-academic career, because one also has learned to attack problems, tackle them in a team, and really push the limits that way.
Thanks, Reiner. Djuna or Richard, is there anything else that you'd like to add? Your advice to an early career student who wants to contribute to the wider dark matter search?
I have something to add, yeah. So I would like to add that I think it would have been important for me to know, and I think it's there's not one good way of becoming a scientist. There is also not one way of being a good scientist. So I, for example, followed kind of a non-traditional path, if you will, into academia. I never thought I would do a PhD, let alone have the job that I have now. And still I love it. So that's okay too, you know. But if you are one of those students that knows early on that you want to be a physicist and you want to study dark matter, that's great, of course. And I would just, I guess it depends a little bit on what you're interested in. If you're interested in experimental physics, there's lots of experiments that have programs for students and ways to get involved from undergrad onwards. And if you're interested in theory, I would say follow your curiosity. The most important thing is to keep learning. I have my best ideas when I am learning things around my subject, not directly targeted at what I already know, but just exploring outside of it and just asking questions. So I would sort of, I would encourage students to do that and just to not be afraid to ask questions. And also to perhaps, read beyond your textbook a little bit, try and open a research paper, go to a research talk sometimes. It doesn't matter if you don't understand most of it. I would be very surprised if you would actually as an undergrad student. But that is a challenge. Maybe that is kind of an interesting challenge. For me, that was an interesting challenge, at least.
Wonderful. And Richard, anything that any advice you'd give to your, your former self or to another student who's considering contributing?
Yeah, so to kind of follow up on what Reiner and Djuna said, one thing that's not always apparent to, I think, undergrad students in particular, there are actually programs, particularly for experimentalists at least. My collaboration, we're always taking on summer students as early as people out of first year physics. So, and it's not really about, being so much, the best math student in the course or whatever. What they're really looking for a lot of the time are just people who are passionate about physics, are interested in the topic and are, generally critical thinkers. So I would just say that, if you think, if you're an undergrad student, maybe in physics, and you're debating doing a master's and you don't know if you want to be an experimentalist, you don't know if you want to go work on cryogenic dark matter searches or go look for neutrinos or whatever, these kinds of summer student positions can really get you a nice feel for what you might want to do in the future and, let you know if research maybe is a nice career avenue for you or not. I think that's probably the advice I would give. Also, like Djuna said, there's never too early a time to kind of start reading research papers or going to seminars, even if you don't understand things. You kind of pick little things up along your way, and that will end up being what makes up a lot of your physics knowledge.
Well said on all accounts. I think that's actually a wonderful note on which to wrap up our Dark Matter Day panel discussion. I'd like to thank each of you for sharing your perspectives and your thoughts on everything we've talked about today, and wish you a happy Dark Matter Day. So with that, I think we're ready to sign off.
Happy Dark Matter Day.
Thank you.
Yeah, bye. Thanks.
Thank you all.